Organic compounds. The division of organic and inorganic in chemistry came from a long time ago, like many things. It's hold over from an earlier time. Compounds that were isolated from things that were alive or had been alive were called organic, and compounds from non-living things were called inorganic. Now, you go to the grocery store and there's organic apples and they cost more than, are the other ones inorganic apples? No, they're just apples that they may have used pesticides on, right? Chemists use the word organic in a much different way than they do at the grocery store. But these organic compounds, as a group, behaved very differently than inorganic compounds. They were more easily decomposed, and early scientists found that they could synthesize, they could make the inorganic compounds in the lab, but they really couldn't make organic compounds very well. Today, organic compounds can be made in the lab, and they are commonly done so, but they're also all over the place. Your body is full of organic compounds. Organic compounds are generally composed of carbon and hydrogen, with oxygen, nitrogen, phosphorus, sulfur. Those are the next most common elements. And then they'll have trace amounts of other elements, but really not much of anything else. The key element is carbon. If it doesn't have carbon in it, it can't be organic. Carbon is really cool because it forms 4 bonds. It has this nice tetrahedral shape that we'll learn about later. And carbon does covalent bonding. You know, carbon's right smack in the middle there. It's 4 over from the noble gases in either direction. And so carbon really doesn't form ions. Group 3A form 3+, and group 5A form 3-. What about group 4? Do they form 4+? No, not really. Carbon forms covalent bonds. And it always forms 4 covalent bonds. Those can be single, double, or triple bonds. It will form bonds with other carbon atoms or with other elements. It's not too particular. And the chemistry of carbon is really, really interesting because the carbon often bonds to other carbon atoms and forms very long chains of carbon atoms. These can be branched. They can incorporate rings. They're just really, really interesting. So here are some examples of organic compounds containing carbons and hydrogens. Here we've got 3 carbons in a row. Here we've got 3 in a row, and then there's this branch off over here. Here are 6 carbon atoms playing ring around the rosy, and the hydrogen atoms are hanging off the outside. We can have a double bond, we can have a triple bond, we can get oxygen involved, all kinds of cool stuff. So there's all compounds, there's inorganic compounds. We've been talking about those, and we'll spend most of the semester talking about those. There's the organic compounds. These are divided into hydrocarbons, which contain hydrogen and carbon. Hydrogen and carbon. That's a good one. Hydrogen and carbon. And then we've got functionalized hydrocarbons. So these have carbon and hydrogen, but then they also have some other things on them. Hydrocarbons contain only carbon and hydrogen, hence the name hydrocarbon, hydro for hydrogen. These make excellent fuels. Oil is going to be mostly hydrocarbons, gasoline, liquid propane, natural gas, all these things we burn for heat and light. Naming hydrocarbons, those that only have single bonds are called alkanes. And if they have a double bond, they're called alkenes. And if they have a triple bond, they're called alkynes. So again, we're using the whole suffix-prefix business. So the hydrocarbon names are a base name that is determined by the number of carbon atoms, and then the suffix is determined by what kind of bonds are present. So here are the prefixes or the base names for the first 10 hydrocarbons. Let's start with 5. Pent, like penta, hex, hept, oct, non, dec. These sound familiar, right? These are very similar to the prefixes we use to name binary molecular compounds. The first 4 are different. We get methane, ethane, propane, and butane. And those are not related to numerical prefixes. And the way I remember them is with a mnemonic: Mom eats pickled bananas. Yes, it's crazy. I don't even know if you can pickle a banana. I am not fond of pickled anything myself. But if Mom's eating pickled bananas, she's probably preggers. M for methane, E for ethane, P for propane, B for butane. I still say that in my head because I cannot for the life of me remember that propane has 3 carbons. But it works. So that tells us how many carbons. Suffix tells us what kinds of bonds there are. Can't read that. So methane has just carbon and hydrogen. Methane means 1 carbon, so it's going to be surrounded by 4 hydrogens. This is the structural formula. This is a space-filling model. Propane is 3 carbons, so there's propane. N-butane. B, Mom eats pickled bananas, that's the 4th one. 4 carbons. Pentane is 5. And so we can just make these straight chains of carbon. The name tells us how many. This is ethene. Because of the double bond, we change ethane to ethene, and this is ethyne. So eth is the prefix meaning 2 carbons, and the triple bond gets it the suffix -ine. Functional groups are little groups that add functionality or chemical character to these hydrocarbons. And it doesn't really matter what the functional group is on, it always has sort of the same chemical and physical characteristic. Even a carbon-carbon double bond or a triple bond can be considered a functional group because it affects how it reacts. So if you have a group of organic compounds that have the same functional group, we call those a family. Alcohols are examples of a functional group family. The alcohol group is the OH group. So here we have a methanol. It has 1 carbon, so the name comes from that. It's methane, and we put an ol ending on the end. So this is a isopropanol. It's got 3 carbons. So I am not going to require you to learn all these guys, but these are the functional groups for organic chemistry. Alcohols, OH, the ethers, aldehydes, ketones, carboxylic acids, esters, and amines. But we should be able to do something like this. Draw the structural formula for nonane. Not no name, nonane. How many carbons does nonane have? 9. So we'll just make a line. We're going for super simple ones here. Straight chains. 4, 5, 6, 7, 8, 9 carbons. Each of the carbons has 4 bonds. It's only got carbon and hydrogen. We've already accounted for the 9 carbons, and so the rest of the 4 bonds are all made up with hydrogens. So these are all the bonds that are going to have hydrogens. And it begins to look like a millipede or something, right? So H's on each of those. And I'm at 9% battery life. I'm not going to write out all the H's. If we have something like this, to which family does this compound belong? We're looking for something besides carbon and hydrogens and single bonds. And we see this C double bond O business in here. Let's go back to that table and see if we can spot something that looks like that. There's this one, and this one, and that one, and that one. Well, these two both have another oxygen, and we didn't see that. This one is an R group, and R just means a bunch of carbons and hydrogens. And this is an H. And if we go look at this one, this carbon is between two other carbons. And so he would be considered a ketone, one of these guys, because the aldehyde would have a hydrogen bonded to the carbon. So that's just kind of an example.